Is not the deficit of the cat to the advantage of the spider? We continue Physics 122, discussing the topics of black-body radiation and quantum mechanics. I will loosely describe black-body radiation by saying that anything that has temperature will emit light. In other words, any object at a temperature greater than absolute zero will give off electromagnetic radiation. We said in a previous section that the idea of color can be quantified by considering either wavelength or frequency. For what we do in this course, we could consider wavelength and frequency to be essentially interchangeable ideas because these two quantities are related to each other through the equation lambda times f equals c, where c is a fundamental constant of nature, the speed of light. Any object that has a temperature will emit light in every color. In other words, any object at a given temperature will emit every wavelength of light, but that object will not shine equally bright in all colors. There is a characteristic black-body spectrum curve that looks something like this. We can see that at certain frequencies, in other words, at certain wavelengths or in certain colors, that object will give off a lot of light, and in other frequencies, that object will give off very little light. A perfect black body is just an idealization. The most accurately measured black body in history was the 2.7 Kelvin black body spectrum of the universe itself. In other words, if you were to take a camera and point that camera at a patch of empty space and record the light that enters that camera, you would see a black body curve to a very high degree of accuracy, to about 1 part in 1,000 or 1 part in 10 to the 5, depending on how you want to consider your experiment. This experiment was performed in the early 90s by the FIRUS instrument on the Kobe satellite, and to a very good approximation, we can treat stars also as black bodies. If we were to point a camera at the sun, then we would see a spectrum that looks something like this red curve on this plot. The valleys in the red plot are due to the presence of various gases in the Earth's atmosphere. Light coming from the sun with a wavelength of around 750 nanometers will be absorbed by oxygen in the Earth's atmosphere. Light with a wavelength of around 900 nanometers will be absorbed by water vapor, and so on. The physics responsible for the valleys on the red plot is the same physics as responsible for the creation of spectral lines when you take an absorption spectrum. However, if we were to fly above the Earth's atmosphere and observe the light coming from the sun, then we would see a spectrum that looks much closer to the yellow plot. This yellow plot does deviate a bit away from a perfect black body spectrum, but it is pretty close. There are various reasons that sunlight does not exhibit a perfect black body spectrum. One example is the fact that the sun itself has an atmosphere, and various gases in the sun's atmosphere could scatter specific wavelengths of light. It turns out that the element helium was discovered on the sun in the 1800s before it was discovered on the Earth. So astronomers were taking the spectrum of light coming from the sun and recognized spectral lines that did not match any known element, so they were able to successfully predict the existence of a new undiscovered element by observing it on the sun first. We said that the total amount of light emitted by a perfect black body depends on that object's temperature. So as a thought experiment, let us imagine we have several perfect black bodies that are identical in every way except they have a different temperature. If we were to record the light coming from those various objects and make a spectrum of that light, then we would see their spectra look something like this. An object with a temperature of 3000 Kelvin will emit every color of light, but it will not emit very much light. An object with a temperature of 5000 Kelvin will emit more light at every wavelength than the object with a temperature of 3000 Kelvin. And an object with a temperature of 6000 Kelvin will emit more light at every wavelength than either the 5000 or the 3000 Kelvin object. A hot object will emit more light than a cold object at every wavelength. In other words, a hot object will give off more light of every color compared to a cooler object. The total light emitted by a perfect black body also depends on that object's surface area, but we will address this fact a couple of slides from now. The main goal of this slide is to emphasize the fact that a hotter black body will shine more brightly than a cooler black body if we assume that both objects have the same surface area. Let us now look at the spectra of the black bodies at the various temperatures shown in this plot, and you might notice that the peak of these spectra seems to shift to the left towards shorter wavelengths as the temperature of these objects increases. An object at a temperature of 4000 Kelvin will give off light at every wavelength, but it gives off more orange light than any other color of light. An object at a temperature of 6000 Kelvin will also give off light at every wavelength, but instead of shining most brightly in the orange part of the spectrum, it will give off more blue light than any other wavelength of light. There is a relationship between the peak wavelength of a perfect black body and the temperature of that perfect black body, and that's described through Wien's law. Wien's law says that the peak wavelength, lambda p, is inversely related to the temperature of that object. From Wien's law, we could see that as the temperature increases, the peak wavelength, the color of light, or the wavelength of light at which that object shines most brightly, is going to move towards shorter and shorter wavelengths. In other words, towards the bluer part of the spectrum. In this equation, lambda p, the peak wavelength, is measured in meters, and T, the temperature of the object, is measured in Kelvin. We can see Wien's law at work in the three pictures from the previous slide. If we imagine that there is a kettle that can be approximated as a perfect black body, and this kettle were placed on a fire, this kettle would be very hot. However, this kettle is not so hot that it is giving off a substantial amount of visible light. This kettle will give off light at all wavelengths, according to the Planck distribution law, but it is not giving off much visible light, so we do not physically see it glowing. If we instead consider a cauldron in a forge, this cauldron is much hotter. Because this cauldron is much hotter, it is giving off enough red light that we can see it glowing red due to blackbody radiation. This cauldron will probably be giving off more infrared light compared to red light, but we cannot see infrared light with our eyes. Although if we were to stand close to this cauldron, we would be able to feel the heat radiating onto our skin. So we can detect that infrared radiation somewhat. This cauldron will also be giving off yellow and green and purple light, but it's giving off more red light than any other color, so that is why we see this cauldron glowing red hot. Now let us consider an even hotter object. This object is emitting more light in the yellow and orange part of the spectrum compared to any other color. This object will emit red light and infrared and violet and ultraviolet light, but because it shines most brightly in the yellow-orange part of the spectrum, we will see this object as being very bright with a yellow-orange color. Provided we are able to approximate an object as a perfect black body, if we are able to measure the peak wavelength of light emitted by that object, in other words, if we can accurately measure the color in which that object shines most brightly, then that is enough information to know the temperature of that object. If I compare the surface of the sun to a piece of glowing hot metal, and if I can measure the peak wavelength of light from these two objects and recognize that the peak wavelength from both of these objects is the same, then I could conclude that these two objects will be at the same temperature. Similarly, if I compare a red hot burner on a stove to the star Betelgeuse, which shines most brightly in red light, and if I notice that these two objects have the same peak wavelength, then I could say that the red hot burner on the stove is the same temperature as the surface of Betelgeuse. On the other hand, if I look at the star Rigel, I see that Rigel appears to be a blue star. Therefore, because Rigel gives off more blue light compared to any other color of light, I could conclude that Rigel will be hotter than the star Betelgeuse or the burner on the stove, or the surface of the sun, or the glowing hot piece of metal. So far in this discussion, we have only compared objects of different temperatures, but objects do also come in different sizes. A larger surface area will allow for more particles of light, in other words, more blackbody radiation in total to be emitted. To make an analogy, let us compare a match to a campfire. Both a match and a campfire have the same temperature, but you feel more heat from the fire because more radiation in total is emitted. Now, a campfire and a match are not good examples of blackbody radiation, but the idea of a larger surface area allowing for more radiation in total to be emitted will imply that a larger object will tend to be brighter than a smaller object, provided both objects are at the same temperature. We said that the color of light emitted depends on the temperature of the object. The total power emitted, in other words, the total amount of energy per second emitted from each square meter of an object, is described by the Stefan-Boltzmann law, J star equals sigma times T to the fourth. Here, sigma is a combination of various fundamental constants of nature, the Boltzmann constant, the speed of light, and Planck's constant, and T is the temperature of that object. So what this means is every second, an object at temperature T will emit this much radiation, sigma times T to the fourth, from each square meter of its surface. If I multiply J star by the area of an object, I will get the total power emitted by that object. As an example, let us consider a sphere of radius r that can be well approximated as a perfect blackbody at temperature T. The rate at which energy is emitted from this object is going to be described as J star times A. J star is the rate at which energy is emitted from each square meter of this object, and A is the total surface area of the object measured in square meters. Because we are considering a sphere of radius r, the area of this object will be 4 pi r squared. However, if we were dealing with a different shaped object, we would need to use a different equation for the surface area of that object. This is the intrinsic luminosity of the object. The luminosity is the total power radiated, in other words, the total amount of energy given off by the object each second, which is measured in watts. The blackbody radiation emitted by the object will fill the space surrounding that object. To an observer that is situated close to the object, that observer would view the object to be very bright as a result of many photons of light emitted from the object entering the observer's eyes. However, to another observer that is very far away from the object, that observer would observe the object to be very faint. This is because the photons that stream away from the object will dilute as they fill the space surrounding the object. Because this distant observer will have many fewer photons entering his eyes, this observer would view the object to be much fainter than the observer that is situated close to the object.